Okay. Can everybody hear me? Hopefully, yes. That's good. So my name is Visa-Valtteri Pimia, also known in the demo scene as Visu, and I am in the groups Trilobit, Quad Trip, PWP, Digital Sound System, and Ivory Labs, and of course in ISO and Jumalauta, like all the cool people are. And today I'm here to talk to you about programming with 8-bit platforms. And first of all, if you thought this is a programming tutorial, you're in the wrong place, because this is actually more about actually making software and the tools you use for those using modern computers. So this is not really a programming tutorial per se for a single 8-bit computer or anything like that, or a game console. What this talk is more of a sort of general approach and method that I and my friends have been using for creating 8-bit computer software for both consoles and computers during like the past few years. And I personally like to use cross-compilers and the power of modern computers and editors instead of having to work with the limitations of the 8-bit platform while writing the software. So I'll sort of try to go through the methodology we used in those. And it's also a sort of brief overview of the state of the art in 2018 for cross-development of 8-bit software. And the areas we'll cover is how do you understand the hardware platform? How do you approach the actual machine you're developing for, be it a computer or a console? How to write and compile code with cross-platform tools. What tools to use for graphics and sound. I will go through some of them, but this is only barely scratching the surface of what's out there, thanks to the internet. And also how to test and debug with emulators and real hardware. So when you've actually compiled your program, how do you actually test it, and what can you use for that? And we're covering only Z80 and 6502-based platforms, which are the two most popular sort of home machine processors from the 8-bit era. But you could basically use this information for any processor, but those are the ones I'm most familiar with, especially the 6502. So that's where I'm going to concentrate. So let's get going. We have what I call the generation advantage, which means an evolution in computing power, information accessibility, and collaboration over the internet. Especially just the collected wisdom of the internet, is things like programming for Japanese game consoles was basically impossible before the internet if you weren't a third-party developer, say for Sega or Nintendo. So just having the access to the hardware, the software, and the knowledge how to program the hardware was not really available to the public or hobbyists like me. We have the power of modern computing platforms. We can calculate stuff on the GPU. We can utilize cloud computing. We can do all sorts of tricks actually producing data for these old machines using these new machines that have many, many times the computing power. And we have the evolution in compiler technology and programming environments. So sort of bringing back what we learned from higher level languages and programming environments and taking that back to the old hardware and targeting them instead. And just general advancements in computer science. We know a lot more about, have a lot more papers on computer graphics, all kinds of compression algorithms, for example, that we can utilize that weren't available in the 90s or 80s. So there's a lot of things we can leverage even on 8-bit platforms. And just the fact that nowadays there's an existing homebrew scene on the internet, and there's collector support for the old hardware, the games, the software. There's a lot more interest out there just from the collector standpoint of preserving information, making it available for people, and just homebrew in general, making new games for game consoles, for example, is exceedingly more popular now than it ever was in the 90s, just because people now actually have the tools and the access. So, and just some more detail on the kind of tools we have available in the modern era for cross-development. We have emulators, the first and foremost. You don't need the actual hardware to run your software. You can emulate it in software instead, running on a different platform, and see the sort of close approximation of the actual hardware and your software running on it. We have the modern compilers, which I'm going to demonstrate as part of this seminar. We're going to show you some integrated development environments, which are like fully featured environments that you can use for developing 8-bit software. And we're going to go through how you can actually create cassette or disk images, so how you can produce actual media for these old machines. Flash cards, which are a cartridge you can rewrite or have multiple cartridge images on a SD card, and you can run that on a cartridge-based machine like the NES or Mega Drive or whatever you have. And the hardcore way, writing EEPROMs, so actually flashing physical ROM chips, that's still an option if you don't have a flash card. We had to go that direction with our group, for example, for Atari 2600. So the only really option we had back then, there were no flash cards, so we had to actually use an 80s EEPROMer and a UV light to erase the chips. And you can always, if none of these are sort of available, you can go the route of designing and building your own data transfer cable and software. For example, Marco Fit had to go this route to produce software for the Sharp MZ700. So it is an option if you have the engineering know-how for that. And the most masochistic approach is to actually turn your cassette image into audio and record that onto a cassette, or use one of those MP3 cassettes with an audio lead and Android, play the WAV file of the cassette data through that, and run it on the actual software. And I see some people laughing, but here's a photo proof of our last demo from Simulatio, where we actually had to do exactly that. So we had the MP3 player cassette that has the audio lead going to an Android phone, put that in the Sharp MZ800 cassette player that's nicely integrated into the computer, and then wait a few minutes, have some tea while your software is running, and then you watch your demo. Simple. Very quick debugging turnaround time as well. So I highly recommend that. And the only reason why we had to do this, none of the emulators are accurate enough for our effects, so we couldn't use the emulators. Even if we had them, they wouldn't run all our effects. So there's still some computers out there where the emulation accuracy isn't, it's not to get the accurate result. So first part, understanding hardware. So you want to make a demo, you want to make a game, you want to do Hello World on your favorite computer, your favorite console. So what do you do first? Well, first you go to Wikipedia. I highly recommend just utilizing the resources on the internet. And usually Wikipedia is where you find this part that I marked in red here. And that's where you find pretty much what you need to get started to understand what the hardware is. You need to understand what the processor or the CPU is. You need to understand what the display chip is if you want to display graphics. You want to understand what the sound chip is if you want to make sound. If there is a sound chip, not every computer has this. Some just make beeps. And what kind of media does this computer have or console? So it might be disk, cassette, or cartridge. That should cover most of them. There's probably some exotic ones out there that I'm not too familiar with. So for example, here we're looking at the Commodore VIC-20, a really popular home computer from the very early 80s. And we can see it has the 6502 processor here. We can see the clock speed for the processor. And we also can see the different kind of memory configurations we can have available, which means that's the space your program has to fit in. So that's interesting. We can find out the storage is cassette tapes and floppy disks. If you want to go for the speed, you go for the disk. And you can find out, oh, the graphics, this is the resolution, this is the color count. We can have 3 bits per pixel here. We can see we have 4 channels of sound, 3 square wave generators, and 1 noise generator, and it's in mono. And we can also see, OK, it accepts tape and floppy disks and cartridges input. So already, just by looking at Wikipedia, I pretty much know the important sort of specs of the hardware without even going into further detail about it. So that's always sort of where I start. And I've done demos for more than 10 8-bits at this point, I think. So surprisingly, this is usually the most effective way of starting, is just to have the most general idea of what it is. And For the processor, you want to understand what the speed is. Doesn't really matter much, like your code underruns or it doesn't run fast. So you might know what the speed is. And what you do care about is how much do you have user memory or the memory available for your programs, be it in ROM, so on actual chips, or in RAM, where you can actually change the memory and load your program in there. And you want to understand what the instruction set is if you want to code in machine code or assembly instead of going for a higher level language. So you'll have to know what the instruction set is. And of course, this sort of expects you to want to actually learn the instruction set if you want to go for the machine language route. Some of these steps take years, some of them take minutes. It's really, there's no really quick sort of way into this except what you already know and what you're willing to learn. So this is what I call your new Bible. The most important thing for any kind of platform, especially an 8-bit that you're approaching, is to understand what the memory layout is like. So in many 8-bits, it's very common that the actual hardware is accessed through memory. So writing a specific memory location will actually change something on the display or toggle something on the audio hardware. So it's like a memory map design instead of going some other way through ports or whatever in modern computers. You just have a big block of memory, and accessing these special addresses, you can access the actual hardware instead of just accessing user memory. So for example, here we have the memory map of the VIC-20, really nicely laid out. You can see in green we have some ROM here. We have the kernel routines, which is like the built-in BIOS of the VIC-20, so we can't really do anything about that. And the thing that interests us on the hardware is this pink part, which is the VIC chip and VIA chip. So that's where actually all the display and sound stuff happens. And this is in red. That's where your program resides in RAM. So this sort of tells us, OK, our program will go into this memory address, and then these will be expansions. So if it's an expanded VIC-20, we can have this extra memory in blue here. And we have the screen memory in here, and all that. Oh, sorry, the character memory. So basically, the memory map is sort of your guiding blueprint into understanding how the machine is laid out, how it is in memory, how big your program can be, built-in blocks of the computer, how it's mapped in the memory. Then you want to understand the display chip. So the important thing you want to know about is the resolution, like how, if you want to do some graphics, what is the maximum resolution of the screen, how many pixels you have to play with on a single screen. Or if there's multiple screen modes, what are the sort of specs of that? You want to find out the color depth, and if there's a palette, is it fixed? Can you change the palette? So your colors, are you dealing with a fixed color set or something you can actually change using the hardware? So you can have custom palette to choose your colors for your pixels for. And you want to understand the different kinds of screen formats. And if there's something like on the NES and C64, for example, sprites, which are small movable sort of game objects on top of the background graphics. So you want to find out, OK, do I just have a frame buffer, or do I also have movable game objects on top of that? So just get a sort of high-level understanding of that. OK, this is the sort of building blocks I have available for me. And also, how much memory do I need for a screen of graphics? How much memory do I need for, say, 1, 8, 16 sprites, all that? Just sort of do the math at this point as possible. Sort of compare that to the memory map and see, OK, on my graphics will probably need this much if I want to do this and not compress or anything. Just how much do I need memory for that? And for the sound chip, you'll want to find out especially how many channels you have available. So do you have only monophonic sound on one channel that you program, or can you do rhythm and lead and bass tracks separately? It all depends on the sound chip that the machine has. Of course, one of the best sound chips is on the C64. You have a really nice programmable sort of dream synth from the 80s with all sorts of cool features like filters and all that. So you might have that kind of things available, like hardware filters or ADSR envelopes and stuff like that. Or you just have a monophonic beeper. It really depends on the machine you're programming for. For example, the Sharp MZ700, that was only just a beeper. and you have to sort of try to make your music sort of bearable to listen, even though you only have one channel available for it. So for Z80 and 6502, I personally used SDCC a lot for Sega Master System. I've used it on Sharp, and I've used it on MSX2 as well. So this produces pretty good code, like the actual machine code from C. So this is a very high-level compiler I can use to program in the C language. So keep it very sort of readable and understandable on a high level. And there's the rest of these, SJASM, PASMO, TriASM, and all that, they are all assemblers. So if you want to go for the machine code route, instead you can use this. But SDCC also comes with its own assembler built in. So if you just want to use it for the machine code, you can do that as well. And for the 6502, which is in Commodore 64 and many other sort of NES, has a similar chip as well. So you can use these to create software for those machines. And the popular C compiler for that is CC65, which I'm going to demonstrate very soon, which is you can target Atari, Apple II, C64, Commodore PET, VIC, NES using that compiler. So I know I also listed some popular assemblers here. I've used DASM on Atari 2600. I've used it on the Atari 8-bits as well. So that's a very, very good cross-assembler. And these all run on Windows or Linux. I think most of them, but all of them are definitely available for Linux. But I've only listed the cross-assemblers here. So there's a bunch of other assemblers that actually run on the target hardware as well. But I'm only sort of trying to concentrate on the sort of cross-development approach here. So writing and compiling code after you sort of have at least a cursory understanding of the hardware and you want to get something happening on the screen and get something compiled. So this is the big step. This might take you a month. This might make you 10 years. This might take you the rest of your life. But if you want to do this, you have to learn to program. So this is actual code from our MSX2 demo here. So as you can see, it's a very nice and high-level C. I'm doing some very tiny memory address placements here, generating some tables because multiplication is slow, because there's no actual multiplication instruction on the processor. So I'm pre-calculating some stuff. Also, detect doesn't work on MSX1. So I can keep it really nice and high level and readable, and sort of it looks exactly like modern code would look on C. Or you can go the hardcore way of writing your code in machine code. Here you can see the actual Z80 instructions on this column here. And here you have the actual bytes that these instructions are then compiled to. So you can always go for the really low level, close to the hardware approach as well. But personally, like, both have their usages. And I'm going to show you some code where you can actually have the sort of high-level, non-speed critical code in C, and then have the really tight code for effects or whatever in inline assembly instead. So you can even mix and match these if you want to. Both of these compilers that I mentioned support this approach as well. So then basically just need to set up a compiler and compile your first program. And that's exactly what we're going to demonstrate here. So let's go to my editor here. Hopefully that's visible. Yes. And here we have a very, if anybody's programmed in C before, everybody knows sort of what this is about. I'm including some standard libraries for input and output. And I have an external symbol, which I'm going to demonstrate soon why I'm doing it that way. And I just have a symbol function for the main entry point of the program. So this is what's called when the program starts. And what this program actually does, it just prints a single line with a line break and returns exit success, which means, OK, the program exited successfully. So the idea here is that I'm introducing an external symbol here from an actual assembly code. So here I have another file called text.s that has an actual, I could have machine code here. I could have whatever I would write in assembly. And here I'm exporting a symbol called _text, which in the C convention is called text here. And I can access that. So this way I can already just on file level mix and match assembly code and C code and just access like variables from C code instead. So if I go here and run this batch file, which first of all compiles this target in C64, C file gets compiled to source, assembly source. I'm assembling that. Then I'm also assembling the text.s with the string data in it. And then I'm calling the linker from C65 to actually link this into a runnable program using the C64 library that contains all the hardware-specific implementations for input and output and stuff like that. So I can just run it like this. And this will run. As you can see, it printed whatever we had in there on the Commodore 64 screen. So the code that was produced by the compiler is a lot more complicated. It has a lot of all kinds of stuff for the linker. So not probably as nearly as readable as the machine code you would write for this kind of function yourself. But this just goes to show that this is what you actually had, and this is what the computer assembler actually got as an input, plus the library, and that produced the actual runnable program. Now that we have this program, we can also just change the target by building this to Commodore PET, for example. So I call the other batch file. The only thing I really changed here is the target. The files are the same, the code is the same, but the end result will look very much different because we're actually running this on a completely different computer now, which is the Commodore PET. So now if I start the PET emulator, as you can see, same result. We get hello world here as well. Different machine, different memory configurations, but the compiler and the library takes care of all that difference for us. So just basically with the same amount of work, I could also target the Apple II or Atari 8-bit computers as well. That's the basic idea behind CC65. And I also have another program here. Let's see, the wrong directory here. So this is for the NES, the Nintendo Entertainment System, and this is a bit different because this machine doesn't have any kind of sort of printing facilities built in, but it does have video memory and it does have editable blocks you can use for building the background graphics out of. So here we just have a simple helper function for actually writing into the video memory on the Nintendo, which requires you set the address that you write to in the hardware, and then you put the actual bytes in the memory. So there has to be sort of a little bit of sort of redirection here. You can't just directly write to video memory. You have to call the hardware with this special helper function from NES lib here to set where are we writing and then push the stuff in here. So we have this little put string helper function here. And here from NES lib, we're setting the palette. So the NES has a palette that you can change. So this is already, in many ways, more advanced than the C64 because you can actually change these colors. You only have 4 colors you can use at a time on a single block, but you can set the text color here by just modifying the palette. And here, with this helper function, you're getting the X and Y coordinate of the screen and then printing some text in there. And then there's also a function that returns whether we're running on a PAL or an NTSC machine, and that will sort of dynamically show which one are we running on. And the last line is just for disabling the display because the NES is disabled by default on the NES lib, so it doesn't actually output any video. And then we just loop eternally here in an infinite loop. So what that looks like is go to the NES emulator here. And here on your favorite console, we can see this program that we wrote. After you compiled it with CC65, you have it running on a NES emulator. You could also use a flash card to run it on the real hardware as well, of course. So that's sort of bare minimum hello world approach, already to 3 platforms from a single, pretty simple code base without even understanding too much about the actual underlying implementation by just cursorily sort of reading the documentation there. So that's one approach of how you can use C to program for 8-bit computers, for example. You don't need any hardware. You can work on a single netbook like this. You don't really need more than that to do some really complex stuff. So how do you then, now that you're sort of had something moving on the screen, maybe something printing there, you probably want to create some data, which is graphics and music for your computer. And these old machines, of course, they have special formats, and they're not. You can't just throw a PNG file in there. You have to be more in the lines of the limitations of the actual machine. So here's some modern tools that I've used a lot, that I know about, and there's a lot more than these on how to sort of create data for these machines and for your program to actually show and play something. So first I'm going to show, many of these are actually designed and developed by demosceners, which is really interesting. So demoscene has a lot of sort of built-in interest for actually developing these kind of tools and publishing them for everybody, because you're kind of scratching your own itch, because you don't really have the official tool chain, or it's out of date, or you just don't have quality tools that are modern available. So first of all, I'm going to show you one of my favorites, which I've used on C64 and MSX a lot, which is called Multipaint. And this is by my friend Matti CCR. Ported this to JavaScript, but this is originally by Dr. Tero Z and Mark, who did some work on this, I think, as well, on processing. And this is basically a clone of Deluxe Paint from Amiga, but this targets different 8-bit machines. As you can see here, this is the sort of different target machines we can use this paint program on. We can use it for Commodore 64 high resolution. We can use it for multicolor to get more colors. We can use it for the +4, Amstrad CPC mode 0 screen mode, MSX1 mode 2 screen mode, ZX Spectrum default mode, and +4 high res. So let's go something where we can nicely see the color clash. Let's go for the C64 high res. So this is originally a processing program running on Java, but this is using processing.js. This is imported to JavaScript, so you can actually run this on your browser. And I have a mirror of this on my server, quad.fi/mp, if you want to try this out for yourself. So you click on that, and then you get this really nice, very, very reminiscent of Deluxe Paint interface here. So you have your painting grid here. So for example, let's just draw something in here. Let's go for the green. So you literally, everybody knows how the paint program works, so I'm not going to go into too much detail about it. If you've ever used Deluxe Paint, you will be very much at home with this. You can turn the grid on and off. You can magnify it to get really start pixel pushing stuff here. If you want to really get down and dirty with the details, you can do that. And you can do some advanced stuff here, like dithering, for example, so you can cheat using this. Like no more handmade dithers. This will just do that for you. And because I'm in high-res mode, where inside one of these grid cells, I can only have 2 colors. So if I have more than 2, I will get this, as you can see, I'll just turn the grid off. You can see this block appearing, and that's because this paint program actually obeys the limitations of the target display mode. So I can't put pixels in any configuration I want. And these blocks appear because I have too many colors in this single grid, 8x8 pixel area. So this is perfect because you can't. It's impossible to paint a picture using this that doesn't work with the actual hardware. So what you see is what you get. This is an actual WYSIWYG editor for the C64. So you can literally use this, and I used this for our assembly demo last year. So all the graphics basically that I made were hand-painted using this, and I used some PNGs as reference. But that's the basic idea. So here's a really good sort of approach of a modern tool, and you can even do stuff like create brushes out of the existing stuff you paint, and then paint using that. And here you can see the speed of JavaScript really. It's not probably not the fastest when you start painting with a big brush like this. But you can do, as you can see, you can do all sorts of crazy stuff with this software. That's really not that easy to do if this was running on a C64. And if you switch the mode, for example, to Spectrum, then you get the really nice, super garish palette here. The screen is a little bit smaller. And once again, the same idea. I can draw something. I'm getting the color clash here. But I can always use that to my advantage to do like maybe some fat bordering or something like that. It's really, I'm not a pixel artist, so I can't really utilize the full power of this program. But there's some really amazing examples on the homepage of this multi-paint software where you can really get the idea that you can really do some really cool looking graphics in this if you have the artistic pixel graphic sort of mentality, which I don't. And then the other program that I want to show is YYChar, however you program that, however you pronounce that, YYChar, Char. I often wondered how the hell you're even supposed to pronounce that, but that's left to your exercise. What it is a very, very convenient Japanese-made graphics editor for all kinds of different kinds of consoles. Here, in this drop-down, you can sort of set the format, and you can edit graphics for the NES, Game Boy, Neo Geo Pocket, Virtual Boy, MSX, Super Nintendo, Game Gear, PC Engine, Game Boy Advance, Mega Drive, MSX, Wonders 1 Color. This does most of the 8 and 16 bits you can think of, especially the Japanese ones, because this is designed by Japanese people. And let's show you the tile set that I used for the example that I showed before. So here's the actual graphic memory data that I used for the small Hello World program on the NES, because the NES doesn't have any character graphics in memory. It doesn't have any letters A to Z in memory. Every game has to program their own sort of way of showing text. So this is what the actual graphics ROM chip will contain. It has this nice cat picture there as well. And you can use this to actually pixel as well. So you can just start editing here, or you can zoom in more and sort of get a better idea on a single sort of glyph here. If you go 16x, you can edit a single glyph really nicely here. So this is what I used for our first NES demo back in 2005. So this has been in my tool chain a long, long time. And I still haven't found anything better than this one, so I always just go back to this in BMP, and then edit that in Photoshop or GIMP or MS Paint or whatever, and then open that back as a BMP into this program if you prefer a more advanced sort of painting program instead of using this really complicated interface. But what you get here is you can really easily see the big pixels, and you can play with the different palettes. And this is the actual color set you can use on the NES to select your colors from. And this is the actual set of 4 that you can use currently, and this changes all the graphics for everything. This is actually the palette that Super Mario uses for the Mario sprite, this last one here. So if these colors look familiar, that's because of it. That's the Mario one. And the next thing I'm going to show you are some screen editors. The one is for the Sharp MZ700, another Japanese software that we found on the internet. And this we found was the best way to get graphics on the MZ700. And as you can see, this program is in Japanese, so you might have some problems understanding these Japanese menus, but it's sort of understandable with trial and error, so it's doable. And here's some example what you can do with this. This is very simple. You only have these characters you can use, and you can set the colors, background and foreground here. So that's the drawing area. So you can't change any of these characters. It's a fixed character set, so you just have to live with that. But here's an example from our demo from Simulatio this year to show the sort of power of this if you're an accomplished graphics artist, who is not me, using this software. So here's some cyberpunk imagery using only this character set. So if I want to edit, I can add some ugly faces in here, which shows you exactly how good I am. But this is what you can do if you're actually a graphically talented person, just using 2 colors for a character and picking from this character set and sort of being clever about it and try to sort of get a style out of it. And here's a noodle stand in the night. You can watch this demo. This is an Ivory Labs demo if you want to see it. And then other screen editor we have is another tool by Markku. And this is for the Commodore 64 and VIC-20 Commodore. This is meant for editing screens in the PET-SCII mode and PET-SCII, like ASCII on the PCs and or the modern hardware. PET-SCII is a sort of version of their own character encoding for the Commodores. So for example, if we want to edit the screen on a Commodore 64, we select that. And here you have the very familiar color scheme of the C64. So you can either just use this as a paint program, like I did before. You can just literally draw using these characters here. Or you can use this in typing mode, which is you press Enter, and then you can start typing text here. So you can just have sort of multiple ways of using this software. You can also do animation using this. There's a lot of different features this program has, and Markku has been using this in many of the FIT demos for the sort of Commodore 8-bits. So this is very convenient. This can export code as well. This can export just the character codes for the screen. So it's very easy to use for creating character graphics for the full screen on these different Commodore machines. So this is highly recommended. It's just called PET-SCII. You can find this on Poet. And then some tools for music. So first we have TIA Tracker for the Atari 2600 from 1977. Yes, we can have a tracker for that. We have Go Tracker for the Commodore 64, the SID chip. Everybody knows the nice synthesizer in that. And then we have Arcos Tracker for Spectrum, MSX, or any kind of PSG-based hardware, which is in multiple computers. We can use Arcos Tracker for that. And these are all running on Windows. And I think all of them are also available. TIA Tracker can run under Wine, and Go Tracker and Arcos are available natively for Mac OS and Linux. So let's go for TIA Tracker first. This will make your ears bleed because the hardware is notoriously out of tune and really, really super basic, being from 1977. So let's make an instrument here quickly. You can only set the volume, start and stop volume, and the frequency of the start and stop. These are all the fixed waveforms that the hardware does. It's extremely limited. You can't change them. You can just select one, and hopefully we can hear our very beautiful music soon from that audio. We can't hear anything, can we? I'm not hearing anything, at least. Let's try something else here. Can we have audio? I'm getting no audio here. Ah, there we are. Yeah, some of these are out of tune as well because the hardware is terrible. So let's listen to our beautiful tune that will make everybody cry from the experience of beauty and happiness. So once again, if you're an actual musician that has even the basis of sound theory behind them, you can probably use this to actually create some bearable music. So let's just have a listen of some real music from Glafuk here. Some people might know this tune, Bump the Bass, Mega Blast. Only on 2 channels this time, though. Enjoy how out of tune that lead sound is. So that's TIA Tracker only for the Atari 2600. So this is probably as the oldest you can go, where you can actually get more than 1 channel. Like, I don't really know anything else except the Atari 2600 for that. And then the next up we have a Go Tracker. Let's see, where is that? I think it's this one. So Go Tracker is by a Finnish guy, actually, though we have what we call Kotikenttä Etu here, right? And this is a tracker for making Commodore 64 music. And let's get some examples here. So most of these obey the same sort of kind of paradigm as other trackers. You have multiple tracks. You have instruments. You have parameters for those instruments. So yeah, you can actually make Commodore 64 music with this, and you have the emulated sound chip here, so you can listen to what it's sort of. This is pretty close what it will sound like on the actual hardware as well. And only 3 channels here. You have to learn and all kinds of effects you can do with this. So feel free to read all that on your spare time if you're interested. This is one of the easiest trackers I found and very popular one for making music. And the guy Lasse Örni who developed this, he used it for games and demos as well. Next up we have Arcos tracker, and this is the one for like Z80-based machines, usually with the PSG chip. And this is like brand new. This came out this spring. And you can import stuff from older trackers using the PSG chip, or you can just like use this to compose new music as well. So we can open all kinds of different formats using this. And once again, we have 3 tracks, instruments. We have some track data here. And this is very nice, sort of GUI-based, nice and visual. And once again, here we go for the music. Oh, let's get something a bit faster than that. That's a very slow song. Let's get something else in here. Find something a bit faster than that. This can do up to 9 channels. If you have 3 sound chips that you can multiplex, you can use this for those kind of machines. So here's some Commodore 64 music, but sort of instead doing it on a PSG chip instead. So you can get sort of close to it, but it's not the same. So this is sort of the non-programmer approach to making music. You can give this to a demo scene musician, and they're probably really happy with these apps to understand how they work, because they can just concentrate on the music part and not really have to understand the technology behind it. They just have to read the instructions on how to make the instruments and all that. So there's sort of 3 similar kind of approaches to making music on 3 very different sound chips with very different limitations. And next thing I want to show you is an IDE, an actual sort of browser-based environment for both writing code, testing code. And this is called 8-Bit Workshop. And this is really one of the most interesting things I've seen in a while. So you go to 8-Bit, that looks very promising. You can do Atari 2600. You can even write code for arcade boards using this IDE. So, OK, let's give it a try. And when you launch this, this is what you see. Let's get the Atari thing first. It's easy to understand. So we go to Atari. And the simplest example, raster bars. Everybody knows raster bars. So here in this left window, we have the actual code. So this is actual 6502 assembly. And in this column, we have the memory address, the line number, and we have the actual bytes that this instruction on this line is assembled to. So this is really, really useful for, especially if you have to cycle count your code, you have to understand how much time your code takes. This last number tells you how many cycles of CPU time this line of code used. And if I edit this all updates in real time. So if I want to change the effect, the only thing I have to do is just start changing the numbers, and I get different results. And this emulator will dynamically just reload the program, and you have this sort of simulated Atari interface here for pressing all the hardware toggles and all that. And here you have sort of the built-in programs. You can also store your programs on the cloud using this, or you can store them locally in files and then use this program to load them back into it. And this is basically a very good way to understand how the Atari works. Like here's a simple game example you can look at. And it's not too many lines of code. It's under 300 lines of code, and you already have 2 cowboys running in front of a background. Not much else, but it's a start. And you can have even more complex stuff like that when you really sort of drill down to it. You can have a nice 3D road effect here, classic sort of what you can do on the Atari. You have a nice dusk evening sky here. But 8-Bit Workshop can do even crazier things. You can also target Midway arcade boards. You can target the Galaxian arcade board. You can now target Williams board and the Atari Vector game. So you can actually use this to dynamically sort of keep iterating on something that will actually run on a real sort of vector display. So here's an example of an emulated hardware architecture display. And you could reasonably take this code, put it on a ROM chip, solder that on an actual arcade board, and see it running on an actual arcade cabinet. So that's what modern technology gives you. Like, it was probably a lot more complicated to do these games back in the 80s, using only machine code and writing on a notepad and keeping most of it in your head and not really using any kind of sort of tools to iterate through this kind of stuff. But here's one approach. I really sort of enjoyed what they did with this. And the next thing I'm going to show you, we already actually touched it on the previous presentation from the programming processing. So processing is not only useful for creating demos for modern platforms. You can just use it to write the actual demo. You can also use that, the power of Java and all the built-in graphics function and all that, to create demo tools for 8-bit machines. So the way I've used this is actually, you already saw this. This program is written in processing, for example. And this program is written in processing too. So there's already two sort of graphics programs coded in processing, open source, that are built with the same way I've sort of found processing to be useful to write demo tools. So here's the demo tool we wrote with Branch for the Sharp demo. And this is a program that takes in a bitmap and tries to sort of fit to the character set. So the idea is for the last effect in our demo, every single scan line, you can change the characters on the screen, but you can't change the actual pixels. So this program sort of tries to fit the existing characters into that scan line and see what's the sort of closest approximation of that. So the only way we really found how can we do this, because the end result is kind of lossy and it will have some noise and glitchy pixels in there. So we brought this program to sort of go through these different kind of vertical and horizontal offsets to see what kind of looks the best and has the least sort of glitches in it. So that's just one example. Writing for a custom screen mode that my friend designed himself by coming up by just like, oh, we could actually make it show bitmaps, even though this tool to do that. And that's all in processing. Not too complicated, only something like 500 lines of code. Or you can do something like this. And if you want to, for example, create some animations, we did an Atari 2600 demo that I'm going to show in the demo show on Saturday. Some spinning cubes, and we couldn't do anything except show some bitmap animation. So this is what I basically did. I just wrote a quick processing program that runs in the actual resolutions and renders the actual bitmaps, animations in the bitmap. I just made the animation in code, and then I just export the frames into the correct sort of display mode we had and use that in the demo. So we just have a little sort of bitmap animation player in there. So I found this really convenient, but just like, OK, I just want to generate a piece of animation, and I don't want to spend all my day in After Effects or whatever animation program, when it's a lot easier just to code that. And I can easily, if I just want to change this a little, I just change the code, rerun it, dump each frame to PNG, and do some additional processing from there. So this is, not only is this a good demo platform, it is also a very good tool platform, because it's in Java, so you can run it on Windows, Linux, OS X, inherently portable and all that. So, and also export to JavaScript. So there's a lot of upsides to using processing for that. So it was really good to see that in the tutorial as well, because I always found that to be one of the best platforms for writing actual tools that are portable, and you can get a visual sort of feedback of what your tool is doing. And here I'm going to show you some advanced debugging for the C64. So this is another demo Sinner tool called C64 Debugger, and I have a video on YouTube for this that I'm going to show you, disable the audio, and sort of explain what's going on here. So what this is, basically, this is an emulator and a development environment and a disassembler and a paint program all in kind of one, designed by a demo group called Samar for their own sort of creating their own demos. So here, for example, we have the monitor. This is the actual code running real time on the C64, and you can see sort of the memory CPU pointing to this address of the memory and running the actual code there. And you have the color of the 8 sprites you have available. You have some information about the sprites, what they're changed, stuff like the screen pointers and stuff like that. And this shows you the actual contents of memory. So here we have like a bitmap of the whole 64 kilobytes of memory. So you have these nice sort of heat maps when the memory changes. So if you have some complex effects going, you can see the pink color sort of flashing on the left side here. That's the memory actually changing in real time while this demo is running. So as you can probably guess from this, this is an invaluable tool if you have bugs or strange glitches on actually understanding what is the machine doing each frame, what is it doing currently, do I have some free memory, like here I see this black area, okay, no, I know that part of the memory is empty, I can put something in there right now. Here, this is like, get the idea what the sound chip is doing, what the waveform on each channel is. And this is just a very cool way to just look at, if you have a demo like mine, you can just actually run this and use this. And this is one of the most powerful features of this. So you can go to the screen and actually draw on it like a paint program on the actual hard emulator while it's running. So I can just change the screen contents by paint tools. And you could also use this to create custom screen modes, for example, placing sprites on the border, opening the border, and then drawing on the sprites yourself. So this is like requires some really advanced thinking to even come up with an idea like this, I'd say. So I found this really, really useful for just actually creating screens for the demo. I use this tool a lot just to actually create stuff for it. Let's see if we had anything else interesting in here. And of course, you can see the actual, like here's a good way. You can see the actual effect running in the frame buffer there. So this pink area, okay, I can tell, okay, this is where the actual effect is going. And here's some screen pointers going on, and you can see what area of the memory is being touched and what isn't. And here's a very cool feature of this memory map. You can zoom in, and you can see the actual values on each slot. So this is like higher magic to me at this point. Like, there's nothing like this for any other platforms, and that's sad. But you can like zoom in and out to a single memory location and see what's happening. You can see the actual value in there, see the actual address of that. And here you can see this effect doesn't have any sprites. You don't see it, but this is what is actually happening to the sprite hardware. So this gives you a really sort of good idea of what is actually happening in there. And for this sort of next scene, you can see this is the character set I use for building this effect. So it's actually pretty simple, just like 32 characters and then changing some colors. And these outlines are the sprites, so I can see the sprites moving on the screen. I can see them going off screen and sort of track their positions really easily, understand where the moving objects are on top of the display graphics. So that's C64 debugger by Samar. Highly recommended if you're ever programming for the C64. As you can see, it just does a lot of things you wouldn't even think are possible for 8-bit sort of development. Then when you actually have your program sort of running, you're happy with how it looks in emulator and all that, you probably want to create an image. So you can use something like Dir Master for the Commodores. You can actually see the Petsky disk like a layout here. So you can see, oh, I have some Tracy Lord pictures here. That's good. I have a BMP viewer, I guess. So a Windows 95 picture, important to have that. So you can use this to insert files into the disk image. You can change it, create a nice directory listing for it if you want to do nice Petsky graphics on the directory list and all that. You can also write cartridge image to flashcard or EEPROM. This is actually what we used for the first NES demo in 2005. So this was designed by my friend Arto in Lahti. So another Finnish piece of hardware. The first publicly available USB programmable NES flashcard called Funky Flashcard. And I know of only one that was ever made. So this is the only copy ever made. So that's what we used for our first NES demo, for example. I loaned this from my friend. And here's a sort of commercially produced, nice, clear green flashcard for the Game Boy instead. So homebrew, commercial. And for the machines that have a disk or tape, you can have this kind of sort of disk drive emulators. This is probably the most popular and best known one, the Ultimate 2 Plus or the 615 port in your C64 or whatever. And you plug this into the disk drive port, and this will just both act as a freezer cartridge, a cheat cartridge, and also has a menu system for switching cassette images and tape images, disk images and tape images. And you can even use this audio lead to hear the emulated disk drive sounds. If you want to hear the disk drive sounds, this will actually emulate it and output it from these audio ports as well. So you can use this to basically replace the floppy disks and all the hassle with transferring disk images and all that. And this one is called the SHX or XXH, something like that. Anyway, but that's for the Atari 8-bit computers, so the same idea. But here, instead of here, you press a button and you get a display on the C64 where you pick the disk images. Here you have this small sort of LED display instead, or character matrix display that you use for selecting the disk images, and you see which disk you've inserted, and you use these small buttons here to switch the disk image. And you can go the masochist way. Here's another picture of that. So we have an Android running a tape image to WAV file program, have that hooked up to a car cassette adapter here, have that in the original tape player, that goes into the C64, and this way you can wait a few minutes again and do the lazy way of testing out your software. And this should pretty much work on any cassette-based machine, except it is slow. And as the last thing I'm just going to want to mention is Shiru's really excellent sort of tutorial on how to program NES games in C. Shiru is a person that's done a lot of NES homebrew games that are really excellent in quality. So I'm just going to drop this link here. If you want to just start from a tutorial, I highly recommend this one. And NES is sort of easy to understand and very well loved in Finland. And if you want a console, that's one place to start from. So this is a really good tutorial for that. So I think that's it. Thanks for listening.